Okay, so let's start with today's discussion. We are going to continue our discussion with the modal decomposition technique using eigenvalues and using diagonalization of our matrix A. So what we are basically continuing our discussion is on modal analysis or modal decomposition based solution of second order ODE. So we saw that if we have a system of equations given by this form where X is basically a vector, it can have as many dimensions as possible. And each one of them is basically a second order differential equation where X double dot represents the double derivative with respect to time. A is a matrix of constant coefficients. X is again the vector, and Ft is basically external function. So here we have seen that what we can do is, depending on whether your A is diagonalizable or defective, if A is diagonalizable, then we can write P inverse AP as matrix of eigenvalues, lambda 1, lambda 2, so on, as a diagonal matrix. Or if it is a defective matrix, that means it does not have all the distinct eigenvalues, then we get a matrix Q, and where we know what Q is and what P is. So here we actually got a Jordan form where this is called a Jordan block. Basically, we got a block diagonal matrix where you have again the eigenvalues in the diagonal. And for the repeated eigenvalues, you have one at the super diagonal element, one as a super diagonal element. So this is a Jordan block. And what we actually got is a block diagonal matrix. And this is basically a diagonal matrix, where matrix or the matrix P is basically obtained by finding the eigenvectors corresponding to each independent eigenvalues and arrange them in a column format. Similarly, Q matrix is obtained by arranging the eigenvectors. So let's say lambda 1 is repeated. So we have got V1 missing from this. And then we have V2.
Professor?
Yeah.
The third entry in the defective matrix, is it lambda 3 or lambda 2?
I mean, it's up to you. How do you want to call it? So let's call as lambda 3. It doesn't matter actually. Whatever you are basically using the subscript, you must be using the similar subscript for the eigenvector. So it will be okay. So depending on the form of matrix A, what we are going to do is we are substituting X is equals to PY in this case, and we are going to substitute X is equals to QY in this case. And when you substitute this in the original second order differential equation, what you actually got is Y double dot is P inverse A P Y plus FT. And here you will get Y double dot as Q inverse A Q Y plus FT. And this basically is simplified as D matrix, which is a diagonal form, plus FT. And here it will be, let's say we call it J, Y plus FT. So this is basically some uncoupled second order ODE. And you know how to solve this basically from the standard solution available for second order ODE. So this is uncoupled second order ODE. So depending on the number of vectors, you have number of independent equations which can be independently solved one at a time. Similarly here, even if we do not have independent equations, but we have seen that we can still solve we can still solve for individual vectors or individual elements using the standard solution form. Let me know if you guys are.
Yeah. I just want to confirm the last lecture equation number 8 is y double dot has the p to -1.
Inverse. We don't call it -1. We call it p inverse.
Yeah.
What is that? What is the issue question you have?
It's missing a one term, the p to -1 term f of t.
Just give me a second. I'm just pulling that last one matrix. Oh yeah, you are right. So here you have p inverse as well. All right, thank you. This was what you are referring to, right? So I saw in the last lecture, this is equation number 8. So what is that problem? What is the issue you are having?
Yeah. I just want to confirm.
Yeah, okay. So yeah, so here has to be P inverse and here has to be Q inverse FT. It will not be just FT. Okay, thank you. Oh, any questions so far, guys? On this basically, on this formulation that we are using to solve a second order ODE. Now, as the example 9.15 we were taking, we actually saw that what we actually got using example 9.15, we have a 2 mass system which are attached using springs. And there is a force vector attached to here. This is K1 constant. This is spring constant K2. This is mass M2. And these are the generalized displacements, X1 and X2. And we figure out that the system of equations is M2 X2 double dot is equals to minus K2 X2 minus X1, and M1 X1 double dot is equals to negative K1 X1 plus K2 X2 minus X1 plus F1T. So this is what we have seen from example 9.15. And if we arrange them in this format, what we actually get is X1 double dot, X2 double dot can be written as negative K1 plus K2 divided by M1. It is a 4 by 4 matrix. Okay. So it will be K2 divided by M1. This is X1, this is X2 plus FT divided by M1, 0. And this will be K2 divided by M2. And this is negative K2 divided by M2. So this is basically what if we arrange them in a matrix form, this is what we will get. Let me know if you guys are following or you're not following it. Is everybody good so far?
Yeah, I follow.
Yes.
Great. Thank you. So this is
rewrite the matrix better, like because last time we used the mass of the matrix, like a diagonal matrix. Will it yield the same result?
Yeah, I already took the inverse. So essentially that if you take the inverse of the mass matrix, it basic and multiply with this thickness matrix, you will end up with these terms. Are you seeing, if I am not making mistake in understanding your question, let me actually go back to my slides here. Okay, so what you are basically saying, not this one actually, just give me a second. Okay, I believe you are referring to this specific formulation, right? And the diagonal matrix, this is the mass matrix, and we take inverse, right? This is what you're talking about? Yeah? So basically, if you take the inverse and multiply that, you will end up with this specific equation. So this is the same thing that we have been doing here. Okay, so what I'm taking the same example problem. I'm trying to redo that formulation, and we'll extend our discussion beyond that. But just wanted to make sure that you guys are understanding it. So this is basically the same form as this. Now I'm going to pick the numbers basically here, the stiffness and the mass of the individual elements. I pick the number, and let's say the mass matrix, or basically the matrix A that you are going to get is, it's same from your textbook example number 9.15. I'm just using the same numbers that they have given for my matrix A, where matrix A is basically stiffness K1 plus K2 divided by M1, and so on. The elements are basically defined like this. So the elements we are getting here is 2, -2. And F is 1, 0. And if you see that there will be some initial conditions that are specified, which is x0, which is x1, 0, and x2, 0. And x dot 0 is 1, 0. Okay. So these are basically the numbers I'm just taking from the textbook. This is the same example number 9.15 we are looking at. Now, till this much, is everybody following it, or is there anybody who is not following what we are doing so far? Everybody is with me so far? Any questions, guys?
Professor, I just came in a bit late. This is an example from last lecture, right?
Yeah, yes. There's an example from the last lecture, but here I'm just plugging the numbers that are provided in there. So we will carry forward our discussion based on this example.
Does that say plus, does that say at the very top? Yeah, over there, plus f of t divided by m1?
Yes. So this whole is vector f, and that is what is given here as ft divided by m1 is 1, basically.
Okay.
Any other questions, guys? So, okay, if there are no questions, so we basically know now that this equation, this differential equation is in this form, where you have a second order ODE, and instead of being able to solve them separately for x1 and x2, we cannot solve it independently because we have a coupled system of equations. The coupling is coming from the off-diagonal terms in the stiffness matrix. So what we are going to do, we are going to do the model decomposition method. But before we apply the model decomposition, we need to find out whether A is diagonalizable or defective. Now, this is the two branches of solution methodology. Whether if it is A is defective, we have to go through this route. If A is diagonalizable, we have to go through this route. So let me actually pick a random student from our list of attendees. Let's say I have here Anthony Cervantes. Can you?
Yeah, I'm here.
Respond. Okay. So if I have to ask you, what is the physical interpretation of these conditions? Initial, these are basically called as initial conditions. So for any nth order ODE, you basically need some initial conditions to solve completely the system of equations. So for example, if I have to solve the second order differential equation, I need some initial conditions. So these are the initial conditions I have got, or basically this is what the example shows, that these are the initial conditions. Can you explain physically what these initial conditions mean or describe?
So as far as like your x0 and your x.0, your x0 is for your positioning
Yeah.
is at 0, and your x.0 is the first derivative, which would be the
Yeah, what is the first derivative of position called as?
the velocity.
Velocity, perfect. So if you just have to interpret the initial condition, what it says that at time t is equals to 0, both mass m1 and m2 are starting from their original positions from x1 equals 0 and x2 equals 0. That is what these initial conditions represent. And what this represents is that at the time t is equal to 0, the velocity, the initial velocities of the two masses are given by this vector, which means that mass m1 is starting with a velocity of 1. There has to be some unit, it may be meter per second, centimeter per second, whatever that unit is, it has to be that unit. So 1 units per second, whatever that unit should be. So that is the velocity or magnitude of the velocity is 1 for mass m1, and for mass m2, it is basically starting with 0 velocity. So you can have 0, 0 as well, which basically means both have initial velocities as 0. The only thing that is causing the system to move is when you apply a force, the mass m1 will move, and then thereafter it will cause motion on other two systems as well. Is everybody following what we are trying to discuss here?
Yeah.
Yep.
Yeah. Okay. So now we basically pick another student from the class. Let's say we have here Emily. Emily.
Hi, yes, I'm here.
Yeah, so I said that if depending on whether A is diagonalizable or defective, you have to follow this route or this route. So how do I know that? How can we estimate whether our A is, or how can we detect our A is diagonalizable or defective? What should we do? Can you describe whether A is diagonalizable or defective?
With that one.
So the hint is that we are basically doing this chapter based on eigenvalues.
I feel like it's diagonalizable. I don't know how to describe it though.
Okay, that's fine. I mean, you can attempt it. We will try to help each other. So how can you basically say a matrix is diagonalizable or defective? So first we need to find the eigenvalues. That's step number 1. But if I got the eigenvalues, and how many eigenvalues are going to be there here, Emily, for these 2x2 matrix? Am I getting 1 eigenvalue or 2 eigenvalues or 3 eigenvalues or 4 eigenvalues? How many eigenvalues are we can expect to get here?
2.
2. Basically, it is a 2x2 system, so we basically will get 2 eigenvalues. So let's actually find the eigenvalues for this. So can somebody tell me how to get the eigenvalues quickly and what the eigenvalues would be? So eigenvalues will be -1 and -6. Everybody is with me so far?
Yes, Professor.
Yeah. So now coming back to our original question, whether our A is diagonalizable or defective. What do you guys think? If we have distinct eigenvalues, then what is the matrix A going to be? Is it going to be diagonalizable or is it going to be defective if I have distinct eigenvalues?
It's diagonalizable.
It's diagonalizable, right, guys?
Yes.
Yeah. So that is what we are basically now. We basically know that we have to follow this route. Is everybody following it, or is everybody seeing what we are trying to do?
Yes,
Yeah.
Professor.
So that is basically we have to figure out whether we have to go through this route or this route. We have to first find the eigenvalues of it. If it comes out to be distinct, that means I am pretty much sure that it is diagonalizable because it has got its eigenvectors which are linearly independent. Can we find the eigenvectors now? Because the next thing is once we get the eigenvalues, we have to find. How do we try to find the eigenvectors? Because we need to construct this matrix P, which basically has the eigenvectors, which needs the eigenvectors to basically construct. So corresponding to -1, let's quickly find its eigenvectors. Let me go to the next sheet. So we'll start with matrix A. Can somebody please mute your mic because I'm hearing some noise. Okay, thank you. So we have this matrix A, and the lambda1 and lambda2 is -1 and -6. So those of you who know how to find it, please quickly do it yourself. And for the rest of you, let's see how to find that. So we are basically to find the eigenvectors, we are solving this equation. Vi equals 0. So we have -5 plus 1, 2, 2, -2 plus 1.
Professor,
Yeah.
I had a quick question on the algebra when you're solving for the eigenvalue.
Okay, go ahead.
Yeah, it's just an algebra question pretty much. So how come you can't just move the -4 onto the other side?
This one to the other side.
Yeah.
So what do I get with, what will I get or what will I obtain with that? I solve a quadratic equation for lambda.
So you can't do that?
And you can do that, let's do it. Lambda plus 2 is equals to 4. This is what you are saying?
Yeah.
Okay, now what? Now how should I find lambdas?
You just said lambda plus 5 equals 4 and lambda plus 2 equals 4.
That doesn't work that way because it has to be like, well, if you put lambda plus 5 equals 4, let's say, and you say lambda plus 2 equals 4, what is the result of this multiplication of lambda plus 5 times lambda plus 2? It will be 16, right? When you multiply lambda plus 5 and lambda plus 2 together, what you will get?
Oh yeah, 16.
So you can't put that, right?
I see, okay. Yeah.
So basically, this is just you expand it. So let me actually tell you what we actually doing. We are, when you try to find a determinant, we are basically going to get a polynomial equation. Since it is a 2 by 2, we are going to get quadratic equation in lambda. And we have to solve for 2 roots. If it is a 3 by 3, we will get a cubic equation in lambda. If it is a 4 by 4, we'll get a 4th order polynomial. So that depending on the nth order matrix, you will get nth degree polynomial that you need to solve. We call this is a characteristic polynomial. So it has to be a polynomial and you're solving for the roots of the polynomial.
Okay, got it.
Okay.
Thank you.
All right, sure. So I hope other guys who are basically finding the eigenvectors have been able to do that. Can you quickly let me know what you are getting? So let's say V lambda 1 2 is 1 assumption. V lambda 1 would be -4 -2 V lambda 1 comma 2, which is basically 0.5 V lambda 0.5. So basically what you actually get is for the first eigenvalue, you are getting as 0.5 and 1. Is everybody following what I'm trying to do?
Yes.
Yeah. And what will be the second eigenvector? Can somebody quickly tell me so that I don't need to do that? By the way, is everybody following it or not? I mean, I'm just trying to make sure that everybody follows the process. We are just trying to solve this equation and for finding the vector V. So we are just using Gaussian elimination. So I put lambda 1 is equals to -1. So that's why when I say -5 minus -1, it will be +1 and +1 because we have eigenvalue as -1. So when I actually use this, then I use elementary row operation here. This is just ERO. And basically what I did, I multiplied this with 2 and add it and basically add the first row on the second row, then I will get all zeros. That means one of that is independent. So I assume that as 1. I can assume any number I like, I choose as 1, and then I pick the other value by solving the first row, and that will be -2 divided by -4 times whatever the assumption is for the second component. And here I got as 0.5. So the eigenvector will be 0.5 and 1. Similarly, if I have to do for my -6, the equations will be -5 plus 6 to -2 plus 6. Vi equals 0. It will be 1, 2, 2, 4. Vi equals 0. And again, if I perform the elementary row operations from the Gaussian elimination technique, if you remember, I'm just going to multiply this with row with 2 and subtract it with the bottom row. What I will get is 1, 2, 0, 0, 0, zeros. So again, I have second component of my lambda 2 is 1. That's an assumption. And the first component would be V lambda 2. The first component would be -2. 2v1. Yeah, -2. Is everybody with me? So the second vector that you will get is -2, 1. So basically what you are going to get is the P matrix, which is going to be V lambda 1 and V lambda 2 will be 0.5, 1, and -2, 1. That is your P matrix. Is everybody with me so far?
Yes.
Maybe it's difficult to quickly catch the pace of what how I'm writing and just understanding. So I'm not sure how it's the best way to, if you are writing it, please let me know that you are writing so that I don't go further than that. I mean, I will stop there and give you some time to think about the process. If you are not writing it and you follow it, then just that should be okay when we are discussing it. So let me know if you are writing it so I can stop my discussion a bit and give you some couple of seconds and then we move forward. So let me ask you again, are you following it so far?
I'm still running it down, Professor.
Okay, so those of you who have finished writing it down, can you quickly check whether P matrix makes sense? Because if P is this, we know that P inverse times A times P has to be diagonal matrix, which will be given by -1, 0, 0, negative. It has to be this. Can somebody quickly check or using MATLAB if you have it open? This is P matrix. A matrix is already known to you. A matrix is this one. So can you quickly confirm that this is what you are getting? Guys, is somebody doing this?
Yeah, I confirmed it. Just got the answer. It's that matrix, -100, -6.
So it is basically you have lambda1 and lambda2. Lambda1 and lambda2 are your -1, -6. They are the diagonal elements and 0 in the off-diagonal terms, right? So what we are actually getting is we actually follow the methodology that we have shown you. If you follow that, you basically will see that you will get y double dot as P inverse APY plus P inverse F. And you know what is P, you know what is A, and you can follow from there. So you basically can solve from there itself. Now, the only thing is the boundary conditions x0 is equals to 0, 0 will be P times y0. So y0 will be P inverse 0, 0. So to solve this differential equation, you need the initial conditions for y, not for x. So basically you have to multiply the initial conditions for y0, and similarly you have to multiply the initial conditions for x0. So I'm not going into the solution of that. That will be a part of your homework problem to actually solve this and see what the solution you are getting. The textbook already solves it for you, but you basically, that means you know that you get the answer, but I would like you guys to go through the solution technique for second order differential equation, refresh that concept and solve it and see whether you're matching the solution or not. That will be part of your homework problem. But what I'm stopping here at this point of time is explaining you the methodology that we have followed it so far. So let me know if anybody has any questions on the methodology that we have followed. From here onwards, it's just solve second order ODE. Second order ODE using standard solution. Any questions so far, guys? Now, also, you will not be able to directly use the textbook example because the this P matrix that the textbook uses will different than what we have got. And the reason being that what is based on the choice of our assumed eigenvector. So we have assumed 1 on both the eigenvectors. The bottom part is 1. Bottom element is 1 for both the eigenvectors. This is not the same for the textbook. So you get different P matrix. But that's fine. I mean, we don't need to have the same choice of, this is based on our choice. We can select whatever we need. And as you see that it is irrespective of your choice, you still get a P matrix, which makes this calculation diagonalizable. That means you have got lambda1 and lambda2 in the diagonal terms, and off diagonal terms are 0. Are you guys with me so far?
Yes, Professor.
Yeah.
Yeah, I follow.
Any questions from you guys?
Professor?
Yes.
So the different P matrix will give the same value of y?
Yes. Yes. Why? Because your eigenvectors are not like, are not going to be the same based on what your assumption is. And if you actually look carefully at this, it is basically, okay, let me actually see what the textbook says. Textbook eigenvector is 1, 2, right? It says 1 on the first and 2 on the second. So if you just multiply this with 2, it basically leads to the same direction, but the numbers point to be different. They are just normalized differently. That's what it is. Other than that, everything is basically the same.
Okay.
Thank you. So as I said, the magnitude of the vectors does not make much of a difference. It is a direction that makes sense. So if you actually normalize it and if you see the directions of this and this should be the same as what the textbook actually assumes. And yeah, so this P matrix is basically obtained using linearly independent eigenvectors. So these are the 2 independent eigenvectors, and we got this diagonalized form, and we know how to solve that. So I'm not going beyond this because this is what you can easily do from your 501 knowledge, or basically you can review that how to solve the second order ODE. So what we have to do next is, let me actually see where we stopped. Okay. So what we have to do next is that we are going to see solution. I mean, this is basically the solution for second order ODE. What if the solution, if the physical system does not lead you to second order ordinary differential equation, it leads you to some, say, like third order or fourth order, or maybe fifth order. So what do we do in that case? Because if we have a higher order differential equation, we do not have a standard solution like we can use for second order ODE. Okay, the thing that what I'm basically saying is, let me go back to the lecture notes to show what we discussed in the last lecture. Just give me a second, guys. Okay, so what I'm basically referring to you is from the last lecture notes. I was telling you that if I have a second order ODE and I've got the initial conditions, then I will plug this solution, and based on the different roots, I will get different cases, and that will give me different solutions depending on what the individual lambda 1 and lambda 2s are. So you get this specific solution for second order ODE. But if the order of ordinary differential equation is third order or fourth order, then what do? We basically do not have this type of solution methodology available to us if the order of the differential equation changes. So here what we are going to do is we are going to use state space concept. State space concept is going to be very useful in reducing any nth order differential equation into a system of n first order differential equations. So what we are going to do next is to see how we can convert a second order differential equation into first order differential equation. So state space concept. So reducing second order ODE to first order ODE. So let me rewrite the equations we have got. So what we have got is x1 double dot, x2 double dot, which is a time derivative of x1 and x2, is A matrix. Let me write it down here. I'm just rewriting the equation from the previous document, a previous sheet. M10. And this is what we have got from the equation we have derived for our spring mass system as negative K1 x1 plus K2 x2 minus x1 plus F1t. And this is our first equation, and M2 x2 double dot is equals to negative K2 x2 minus x1. This is our second equation, and we have got x1 at time 0 is given as 0, x2 of 0 as 0, x1 dot at 0 as 1, and x2 dot at 0 as 0. Is everybody with me? So, I mean, I just rewrote the equations for the physical system. This is M1, this is force F1, this is spring constant K1. Yeah, everybody is with me so far?
Yes, Professor.
Yeah.
Okay, great. Okay, so I just rewrote these equations. Now, what the state space concept says that Given the number of initial conditions you have, you pick one variable for each of these initial conditions. So pick one for this initial condition, one variable for this initial condition, another variable for this initial condition, another variable for this initial condition. Okay, so choose one state variable for each initial condition. This is step number 1. And then step number 2 is rewrite the original differential equation. Rewrite the original nth order. For us, it is second order at this point of time. It doesn't matter, it is second order, third order, fourth order, it can be any order. So I'm saying nth order ODE in rewrite original nth order differential equation in a system of first order ODEs using state variables. So how to do that? So what I'm going to do, so what we are basically mean by this is we are going to write our equation as F1 something, U2 dot is F2 something, where something in here is U1 and so on. It can be different parameters can be there. So it can be U1, U2, and it can have any time. So it can have any parameters. We will see what parameters are, but each one of them is having only one derivative, which is the first derivative of the state variables, U4 dot and so on till you get UN dot, which is n first order ODEs. N first order ODEs. Now how to get that? So let's do this for our example. So in our example, we have got 4 initial conditions. That means we have 4 state variables, one for each one of them. It doesn't matter whether you select U1 as this or U2 as this or U3. It doesn't matter. The order does not matter. You have to select one for each. Now, after you select one for each, now how to rewrite the equations. We have got only 2 equations, and we are trying to get 4 equations because we have 4 variables. So how to do that? So you will see that U1 is basically X1. Okay, let me also state that U1 is just not this. It is basically U1 is for one initial condition. U1 will be X1, U2 is X2, U3 is X1 dot, and U4 is X2 dot. So that is what your assumption is. The variables basically represent the original variables we have in our original equation. So U1 basically represents X1, U2 represents X2, U3 represents X1 dot, and U4 represents X2 dot. Is everybody with me so far?
Yeah.
Yeah. So the 2 equations that I'm originally getting are from here itself. So what it is saying that U3 is X1 dot or is equals to U1 dot. So basically I got one of the equation as U1 dot is equals to U3. Similarly from here, U4 I have selected as X2 dot. X2 is basically my U2. So I can represent it as U2 dot. So eventually I got another equation with U2 dot is equals to U4. So this is my, let's say, 3rd equation and 4th equation. Are you following it so far?
Yeah.
Yeah. Is everybody with me so far?
Yes.
Take time. If you are still taking time to read or to write or to take notes, please take it and take your time and let me know once you finish it and you understand it or you're understanding it or not. So I have choose one state variable for each initial conditions, but each variable has some relation with the original variables. Our original variables was X1 and X2. So when I select U1, I select U1 as my X1, U2 as my X2. Now I add 2 more variables, which represents the velocity for X1 and velocity for X2. So U3 is equals to X1 dot and U4 is equals to X2 dot. So these are the choice I made. And then I'm rewriting the nth order, basically second order ODE into first order ODE. So at least from these two equations, I can write it as this in this form. Is everybody with me so far? Yeah.
Yeah.
Now pick this second equation. Now see what is the form. It says M2 times X2 double dot. X2 double dot is what? X2 dot is U4. Then I can write this. Let me actually write this here. Negative K2 X2 minus X1. I can write it as M2 X2 dot, which is U4 dot is equals to negative K2 U2 is X2 minus U1. Or I can take M2 there. So it gets U4 dot is equals to negative K2 divided by M2 U2 minus U1. This is equation number 5. Are you getting that? Are you guys with me?
I'm still writing.
Yeah, okay. Sorry. Sorry, I actually didn't give you time to write. Let me know once you are done so we can discuss. And if you are just writing, let me actually take this equation and write it as well so we can explain together. M1 x1 double dot is equals to negative K1 plus K2 x1 plus K2 x2 plus F1 T M1 U3 dot negative K1 plus K2 U1 plus K2 U2 plus F1 T or U3 dot is equals to negative K1 plus K2 divided by M1 U1 plus K2 by M1 U2 plus F1 T divided by M1. This is my sixth equation. So I just based on what I use this second equation, I use the first equation as well. And instead of using x1 variables, I am using the state space variables, u3. So instead of x1 double dot, I am saying u3 dot. U3 is itself is x1 dot. So u3 dot will be x1 double dot. So let me write here, u3 dot will be x1 double dot and u4 dot would be x2 double dot. So once you finish writing, let me know and I will try to explain. And those of you who have already understood what we are doing, I would ask them to write these 3, 4, and 5, and 6 in matrix form. In matrix form means you have U dots on left-hand side and all the other things on the right-hand side. So write it on the matrix form and we will see whether it matches with what we are doing. And those of you who are writing, once you finish writing, let me know, please.
Done writing.
Yeah. What about others, guys? Is there anybody who is still writing?
I'm just copying down the last line.
Okay. So yeah, let me know just once you're done. Yeah, guys, have you finished writing?
Yes, I just finished.
Okay. So again, recapping what we are saying. So we have this original second order differential equation. We have got 4 initial conditions because we have 2 variables here and each one of them has second order differential equation. So we need 2 initial conditions for each of these variables. So I got 4 initial conditions. Now what we are doing for each of these initial conditions, I select one variable. So for this, I select U1 variable, state variable, calling that a state variable, and that I'm saying U1 is equal to X1. Here U2 is equals to X2, sorry. U3 is equals to X1 dot, U4 is equals to X2 dot. X1 dot basically means velocity of X mass 1 and U4 is velocity of mass 2. Now, if I take a time derivative of this equation, I will get U3 dot is X1 double dot. And if I get a time derivative of U4, I will get U4 dot as X2 double dot. So eventually I have basically what U1, U2, U3, U4. And what I want as a step 2 is that I have to rewrite these two equations in a form such that I have state variables, the first derivative of state variables on one side and all the other terms on the right hand side. So what I took, I just take this equation first, U3 is equals to X1 dot, and I know X1 dot is basically nothing but the time derivative of U1. So I just write U3 is U1 dot, and just rearranging, I take U1 dot as U3. Similarly, U2 dot is U4. Is everybody with me so far on this two term equations?
Yes.
Everybody's following it?
Yes.
Great. Now the next thing what I did, I use this equation and I rewrite it using state variable. So X2 double dot. X2 double dot is basically given by U4 dot. So I have M2 times U4 dot and negative K2 X2 minus X1. So X2 minus X1 is basically U2 minus U. So I have U2 minus U. So I just rewrite it in this form. Everybody agrees with me?
Yes.
And similarly from the first equation, I write it instead of X1 double dot, I'm using U3 dot. So M1 times U3 dot is this specific terms. And similarly, if I take M1 on the denominator, it will be basically this equation number 6. So I got 3, 4, 5, and 6. And if you look at these equations, you will see that each one of these equations is basically a first order differential equation in state variables. So this is a first order differential equation. This is a first order differential equation. This is a first order differential equation. This is also a first order differential equation. So I can write them in a matrix form. So those of you who have finished writing in matrix form, let me actually do that and we see if we are making mistake or not. So this is step number 3. Write the first order ODE in matrix form. So you see how much important the matrices play a role. So that's why we have taken a long time in trying to understand the matrices. So matrices form, and we'll keep on doing that for most of this course here. U2 dot, U3 dot, U4 dot. And it should be in the form of U1, U2, U3, U4, plus 0, 0, F by M1, 0. U1 dot is 0, 0, 1, 0. U2 dot is 0, 0, 0, 1. U3 dot is negative K1 plus K2. Sorry, I have that much space, so I'm squeezing everything here. K2 by M1, 0, 0. I don't know whether it is visible to you or eligible or is readable or not, but I'm just using this equation and trying to plug the different positions. And U4 dot would be K2 by M2, U1, negative K2 by M2, 0, 0. Let me know if you are understanding. So let me actually rewrite these equations or rewrite this matrix. The matrix basically looks like this. 0, 0, 1, 0, 0, 0, 0, 1, negative K1 plus K2 divided by M1, K2 divided by M1, 0, 0. Then you have K2 divided by M2 negative K2 divided by M2, 0, 0. Okay, it should be more readable than the first one. Yeah.
Yes.
Yeah.
So is everybody following it, what we are doing here?
Yes.
So what we have seen, we have got that instead of solving second order ordinary differential equation, now if you solve this, which is a first order differential equation, linear, because you have got a matrix A and you have got constant term here. So it is linear because the variables that you are getting on the right hand side are basically not coupled, and they are they are linear in U1. The equations are linear in U1, U2, U3, and U4. So basically we have got a linear system of equations, first order differential equations. And to solve that, there is a specific solution for that. Let me actually write that. So if you have a system of linear system of first order ODE. If we have a linear system of first order ODE where X dot is equals to A matrix X plus ft. Now this is a different, this is first order. So the solution for that is given by X is equals to X of time t is equals to, let me look at the form. Yeah, is EAT plus 0 to time t f tau E A t minus tau d tau. This is the general solution for a linear system of first order ODE. Now this is the same solution that you would have seen in 501 if you are just dealing with one variable, but here we are dealing with a linear system, we are dealing with matrices. So let me actually say what we actually wrote in the first instance. So our equations was U1 dot, U2 dot, U3 dot, and U4 dot. Let me rewrite it again. K2 divided by M2 negative K2 divided by M2 0, 0. U1, U2, U3, U4 plus 0, 0 F by M1, 0. So this is basically, I'm copying these matrices from the previous sheet. So if you have a system of ordinary differential equations, first order ordinary differential equations, then the solution of that vectors x at time t is given by this specific expression where EAT is called as matrix exponential, because E raised to power the matrix. So we have seen so far E raised to power the scalars, but now we have a matrix. So it is called as matrix exponential. And to solve that matrix exponential, it depends on, again, PE dt P inverse. And just give me a second, let me reconfirm I'm writing the correct expression for the matrix exponential. Just give me a second. Yeah, okay. I was just confirming from the textbook that whether this expression is correct or not. So this is Q E J T Q inverse if my A matrix is diagonalizable and if A is defective. So this is how you can basically calculate matrix exponential. Matrix exponential is if A is your diagonalizable matrix, then it is P times E dt, E raised to power dt, P inverse, and E dt is basically E lambda 1t 0 0 0 0 E lambda 2t 0 0 0 0 E lambda 3t 3 lambda 1 lambda 2 are basically the eigenvalues, and so on till E lambda nt. Do you see what I'm saying? So it is basically a diagonal matrix, and EJT would basically be E dt times E delta t. E dt is the same as this, and E delta t is given by I plus delta times t plus delta square t square by 2 factorial, and so on. And let me actually explain what delta would be. I will just explain those terms in a bit, but let me first go through our original set of equations, that's state space equations. So before I actually tell you exactly what EXAT matrix exponential is and how to calculate that, I'm just recapping what we have discussed. So if we have a linear system of first order differential equations where x dot, the first derivative, excuse me, first derivative of the variable, and that first derivative of the variable is here, and this is basically linear system of equations. So if you look at this, what we have got is basically the same form as this, where our matrix, this is our matrix A now. This is the same as my x dot. This is the same as my x here. And this is my force vector, or basically another vector, which is a constant coefficient, a function of time only. So let me know if you guys are following this much or not. Are you guys following it so far?
Yeah, I follow.
Yes.
That's guys, you are following only this much. We're going to explain afterwards what we are doing. But at this point of time, are you getting what I'm writing it here and whether what we are doing it? So let me actually go back. What we have done, we are basically trying to convert this second order differential equation into first order differential equation. And we were successful in doing that by doing choosing this type of state space variables. And once we have got this first order differential equation, then we know that the solution for first order differential equation exists. So if the solution for first order differential equation exists, then solution for these equations will also exist. It will be the same as this. Now, instead of x, I will replace it by u. So u of t is basically E of a t, which is this matrix, plus 0 to time t, the integral f at a different variable tau, E a t minus tau d tau. So A matrix is this, F matrix is this, F of t matrix is this. So basically I got a solution for this system of equations, right? So what it basically means that even if I have, if I go back, if I have a second order differential equation, I get this system of equation. If I got third order differential equation, I still can reduce them using these state space variables into first order differential equation. If I have fourth order differential equation, you will find this in, let's say, if you have, if you remember from the strength of materials or deformables concept, the equation of the deflection is fourth order differential equation. So for the beam, for simply supported beam or cantilever beam, you have a deflection, and if you want to solve for that, it is a higher order differential equation. Similarly, there can be many instances we have higher order differential equations. And if you have higher order differential equations, you can convert them into first order differential equations. And once you convert them into first order differential equations, then you know the solution for that first order differential equation is like this. So you can basically solve that first order differential equation. Are you getting this much, what we are discussing here?
Yeah.
Yeah.
Any? Sorry, come again.
You also need to solve for tau, right?
Sorry, your voice is breaking. Can you speak bit? Can you please speak a bit louder?
Tau, like an integral, that's f of tau, or we need to solve for tau, the variable.
I'm really sorry. Can we type in the chat window, because I am unable to hear exactly what you are asking. So if you can type in the chat window, probably I can pick your question.
I'm saying the tau, like on the
Okay.
integral, the tau.
Yeah, tau is a variable. Yeah, it is basically a variable in the integral. So it is just like f of t. Instead of f of t, you are going to f of tau. So instead of t here, you are going to represent this tau. So for example, if f of t is sine of t, so you are going to use sine of tau here in this expression.
So the tau is basically
Tau is a dummy variable. It is just a dummy variable for time. Dummy variable for integration. That's it. Nothing else. Does it make sense? These are just dummy variable for integration for time with respect to time. Okay, so let me know if you have, it's still not making sense. We will actually explain it again, but just to complete the thought process we are doing. So what we are saying that if you have a second order differential equation, you know how to do that. You basically know how to solve it. So basically we have seen that, okay, so if we have a second order differential equation, we know that we can solve it whether the matrix is diagonalizable or defective, and we can basically construct the eigenvectors P or Q matrix, and then we can make it diagonal by having individual second order differential equations in this form, and we can solve them independently. But now what we are saying that if we do not have a second order differential equation, but we have third order, fourth order, we do not know how to solve them individually itself. We cannot do this diagonalization and solve them because we don't know how to solve them. So what we can do is we can use this state space concept to convert any different order differential equation into a set of first order differential equations. And the reason we can do that, because we know the solution exists for first order differential equation, we know how to solve them. So if we can convert a higher order differential equation into first order differential equation, then we can solve them. And this is the solution process. Now I have just written some terms here like matrix exponential here. Now I was just explaining to you how to compute the matrix exponential. Is basically the matrix exponential is computed as, again, we need to find the P matrix and the D matrix if it is diagonalizable, and Q and J if it is defective. And this is how we can compute it. But I don't think we have sufficient time right now remaining to further discuss about the process of evaluating this matrix exponential. So we will continue our discussion on this matrix exponential, but let me know if you have any questions on the formulation part or any of the part that we have done so far.